This is working. Let me share sound too with my screen. So you have a natural water table. Water is extracted by a water supply well. Sent to an injection plant. Water is then pumped into an injection well. It is then injected into the formation. That's the process of water flooding. And that's just the general concept of it. So here's some basic water oil flow properties where you have the wettability. That's the interaction of two immiscible phases such as oil and water and a solid surface. Solid surface is taken as a smooth, flat surface, and then you have rock wettability, where you have surface tension of the oil minus surface tension of the water is equal to that's equal to the surface tension of water oil times the cosine, so your contact angle. So that's the Young-Dupre equation. You'll notice the different contact angles in a water wet and an oil wet. Other basic water oil properties, you have imbibition, where the wetting phase displaces the non-wetting phase. You have drainage, where the non-wetting phase displaces the wetting phase. Then you have hysteresis, which is the value of a physical property that lags behind changes in the effects causing it. Imbibition displacement test, there's a procedure on it, and that's written by Amit. So the core plug is immersed in oil. The volume of water is displaced by the imbibition of oil measured after 20 hours of immersion. The centrifuge under kerosene and a total volume of water is displaced and measured. The centrifuge in water and the total volume of oil is displaced and measured. The higher the displacement ratio of water to oil, it's water, right? Water wet. The higher the displacement ratio of oil to water, it's oil wet. So there's other methods of detecting determining wettability. You have the capillarimetric method. Fluid will displace other through a glass capillary. The limitation is glass is assumed to be representative of reservoir rock. Then you have the wettability number and apparent contact angle, which is the displacement of water by oil and displacement of oil by air. Then you have NMR, or nuclear magnetic relaxation. The rock sample is exposed to a strong magnetic field and then a weak magnetic field. Lost magnetism rate is measured, which is the relaxation. The linear relation is observed between the relaxation rate and the fractional oil wet surface area. Then you have relative water wettability. The rock is covered by water and is considered water wet if methylene blue is adsorbed. For fluid distribution, the pore geometry is imperative, especially when determining water flooding projects. You'll notice the chart on the left, or the picture on the left, shows breakthrough versus later in the water flood life of where water is penetrating. And then on the chart on the right, you have your water drive early in the drive, midway in the drive, and then when the water's flooded out. Then you'll also notice about how oil is, well, the effects of oil in your pore space too. Early in the drive, you have a lot of oil. Midway in the drive, you have not as much oil. And then when you reach the economic limit, you have some residual oil. Other concepts for your basic water oil properties are your capillary pressure, pressure of the non-wetting phase minus the pressure of the wetting phase, then relative permeability, which is the effective permeability divided by specific base permeability. So the ability of the porous system to conduct one fluid when the other phases are present. Then you have connate water saturation, where the water saturation existing in the reservoir at discovery. And then you have methods of measuring water oil flow properties. You have a flood pot test. Cylindrical core samples are flooded inside out. You have steady state tests. And then you have external drive techniques, which is the Buckley-Leverett frontal advance equation. Here's the frontal advance theory of fractional flow. So you have the fractional flow of water and how it's reduced to, and what's the ultimate equation. So mobility is related. Your relative permeability is related. And really it reduces down to your water rate divided by your total liquid rate. Here are some examples of the fractional flow curves in a water wet rock and in an oil wet rock, where the time to break through is a lot tougher for one versus the other. So you have the frontal advance equation. And the rate of the advance of a plane of fixed water saturation is equal to the total of fluid velocity multiplied by the change in composition of the flowing stream caused by a small change in the saturation of the displacing fluid. Then you have water tonguing, which is contrary to the frontal advance equation. This is focused on edge water encroachment, but the theory could be applied for horizontal system. Water displaces oil by underrunning the oil tonguing. So this is relevant for some experiments, but Buckley-Leverett is successful for all results. Then you have viscous fingering, which is the existence of fingers or discrete streams of displacing water moving through oil. The mobility of connate water. In water wet rocks, it is possible to have connate water displace an oil which itself is displaced by injected water. So there's not enough studies for oil wet rocks. So you have the practical application of the frontal advancement theory, where you have water where you have recovery at water breakthrough. And then you have performance at water breakthrough. The tangent at point at your water saturation 2 represents the water saturation at the producing end of the system. The fractional flow at the point of tangency is the producing water cut. The saturation at which the tangent intersects your fractional flow equals 1 is the average water saturation. Then the inverse slope of the tangent is equal to the cumulative injected fluid in the pore volumes, or your QI. Then you have saturation distribution during water flooding. And then you have the modification for the presence of a mobile connate water saturation, which is this relation below. Now I'm going to talk about oil displacement efficiency. So the tangent point SW2 represents the water saturation at the producing end of the system. The value of the fractional flow at the point of tangency is the producing water cut. Saturation at which the tangent intersects FW1 is the average water saturation. So this is everything I mentioned before. And then the inverse slope of the tangent is equal to the cumulative fluid of the injection volumes, or QI. So there's other concepts of oil displacement efficiency. Rock rotability on oil production performance is much more efficient than when the wetting phase displaces a non-wetting phase than the other way around. You have oil and water viscosities, or higher oil viscosity results in less efficient displacement. And then you have formation dip and rate, where the water displaces oil up dip, more efficient displacement at lower rates, and then higher rates the other way around. And then as dip increases, the efficiency increases up dip and decreases down dip. Then you have initial gas saturation, where it depends on the magnitude of trapped gas existing at the water flood front. So then we have the mobility of displacing fluid, or water, divided by the mobility of displaced fluid. So in the fractional flow equation, the ratio of the relative perm is the ratio of one given saturation, or 1 point in the reservoir. In the mobility ratio equation, the water perm is that in the water in the contacted portion of the reservoir, and the oil permeability is that in the oil bank, where there are two different points in the reservoir. So here are your effective oil viscosity on the water-oil mobility ratio, assuming a water viscosity of 0.5 centipoise. Notice how the mobility is reduced at the water rate, water wet compared to the oil wet at different viscosities. Now, the chart on the right, you have your mobility ratio and the breakthrough at aerial sweep efficiency. And that was assuming a 5-spot pattern. So for aerial sweep efficiency, the percent of total oil reservoir or pore volume is within the area being swept by water. So here are the different patterns of water flooding, the ratio of producing wells to injection wells, and then the drilling pattern that's required. So I'll take a moment for you guys to read that. And then here's more visuals in terms of the different patterns for water flooding. So triangles an injection well, the circle's a production well. And then your dotted line or your dashed line is a pattern boundary. So you have the regular 4-spot, skewed 4-spot, 5-spot, normal 9-spot, inverted 9-spot, direct line drive, staggered line drive, 7-spot, and an inverted 7-spot. So for prediction methods, for an aerial sweep efficiency, you have the Dyes et al., which is a displaceable volume and fraction of the total flow coming from the swept portion of the pattern. That can calculate the total oil recovery from the pattern, aerial sweep efficiency, and flood displacement efficiency. You have producing water-oil ratio, assuming water is only being produced from the swept region. You have cumulative injected water volume. And then you have Craig et al., which is a prediction for 5-spot pattern. And then Rappaport et al., which is the compared 5-spot pattern with the linear system. Then you have Pratt et al., which is a 5-spot pattern, assumed a piston-like displacement. So it's been the evolution of some of the founders of water flooding, or advancing our understanding. You have other factors affecting aerial sweep efficiency. You have cross flooding. You have direct, so cross flooding of different water floods of different injectors. You have directional permeability of the heterogeneity to different permeability. You have formation dip, which sweep is affected, but the fluid injectivities are not. You have off-pattern wells in which the oil recovery at breakthrough is always lower than an off-pattern injection well. You have sweep beyond the normal well pattern. You have end-to-end flooding, and then you have horizontal fractures. Then you have factors selecting a selection for a water flood pattern. You have to provide desired oil production capacity, provide sufficient water injection rate to yield desired oil productivity, maximize oil recovery with the minimum of water production, take advantage of known reservoir non-uniformities such as directional permeability, regional permeability differences, formation fractures, dip, etc., and then be compatible with existing well patterns and require a minimum of new wells. And then be compatible with flooding operations of other operators in adjacent leases. So you have different types of heterogeneity, such as aerial permeability, vertical permeability, and then reservoir scale fractures and directional permeability. The quantification you have is a conformance factor, which is the portion of the reservoir contacted by the injected fluid, which combines aerial and vertical sweep effects. Then you have a positional approach, which is using core perm to define layer properties. You have the coefficient of permeability variation. You have perm ordering. Then you have the Lorentz coefficient, which characterizes the permeability distribution within a pay section. You have averaging permeabilities. You have statistical zonation techniques, and then you have geological zonation. So then I'll talk about vertical and volumetric sweep efficiencies. The vertical sweep efficiency is the measure of two-dimensional effects of reservoir non-uniformities. And then you have the volumetric sweep efficiency, which is the pore volume contacted by the injected fluid, divided by the total pore volume of a pattern of a portion of a reservoir of interest. So then you have the mobility ratio influence, which is this relation right here. And then RWO is the radius of the leading edge of the water bank, the water oil interface. Chart below shows the relative injectivity at different flood fronts under different mobility ratios. Then you have other charts here where you have a variation of fluid injectivity in the liquid saturated 5 spot, 40 acre 5 spot, and a 1 foot diameter wellbore. And then you have fluid injectivity contrast in a 2-layered liquid radial filled system. Then you have the influence of gravity forces, which is the degree of gravity segregation of the injected fluid, measured in terms of the volumetric sweep efficiency at breakthrough. So it depends upon the ratio of viscous forces to gravity forces, and then higher rates or higher volumetric sweeps. So the chart below just shows the volumetric sweep efficiency at breakthrough. So the linear line is the uniform system with gravity effects, that's straight line. And then the flat line is the uniform system with no gravity effects. So this is the effect of non-uniformity on gravity effects with the set mobility ratio. So now I'll talk about the influence of capillary forces. The highest oil recovery was obtained at the lowest simulated water injection rate. The difference of performance depended if more permeable layer was at the top or bottom. And then due to capillary pressure, the volume of oil produced at a given injected water volume decrease slightly with the rate whenever there's a significant increase in water oil ratio. And then you have the influence of crossflow, which tends to improve the recovery performance at a favorable mobility ratio, but the reverse occurs at unfavorable mobility ratios. So you have the rate effects on volumetric sweep efficiency, the range of rock perm within a specific reservoir. The rock's attraction to the wetting phase is stronger the lower the permeability, but the ease of flow also decreases. The size and location of less permeable zones, this will control the number of opportunities for the injected water to imbibe in the streaks. Isolated, dispersed, and tighter lenses will allow more imbibition, and thus higher oil displacement will occur if low permeability rock exists in a thick continuous zone. And then the wettability preference of the reservoir rock, the rate of imbibition will depend directly upon the degree of the rock's wettability preference for water. So then the effect of layer selection on volumetric sweep calculations. Large number of layers. The most permeable layer will have the higher absolute perm value so that the early water breakthrough into the production can be expected. Choosing a small number of layers can sometimes result in predicted performance approaching that of a uniform system. And then you could choose a number of layers based on equal flow capacity or equal KH. So this can control early water oil ratio and breakthrough time. So you have methods of predicting water flood performance, which is reservoir heterogeneity, aerial sweep effects, numerical methods, and empirical methods. So reservoir heterogeneity, methods concerned with the effects of varying injectivity layer by layer in the radial portion of the reservoir surrounding the injection well. Methods concerned with oil recovery layer by layer. Methods that characterize reservoir non-uniformities by their perm distribution and calculate the overall effect. Euster's Suter-Calhoun method of water flood has 3 stages: radial outward interference with other water floods, and then constant water injectivity. Pratt's methods, Jewett-Baker method, it's added combined effects of mobility ratio and aerial sweep efficiency. Stiles method accounts for different flood front positions in liquid field linear layers having different permeabilities. And then the Dijkstra-Parsons method is the correlation between water flood recovery and mobility ratio and perm distribution. For aerial sweep, you have the Muscat method. The streamline and isopotential distributions and various flooding patterns yielded aerial sweep efficiency at water breakthrough for a unit mobility ratio. You have the Hurst method, which is an increase in area sweep efficiency obtainable after water breakthrough by a continued water injection. You have the Cottle method, which is focused on 4-spot, 5-spot, 9-spot, 7-spot, and line drive patterns. You have the Aronofsky method, which is a 5-spot and line drive method, and then aerial sweep efficiency as a function of mobility ratio. Then you have the Depp-Hopper method, which is a 5-spot and line drive methods and other patterns displacement. It took place along stream tubes and joint injection to production wells, and that assumed that oil saturation was reduced to residual oil saturation at the flood front. Then you have prediction methods focused on displacement. So you have Buckley-Leverett. You have Craig, Geffen, and Morse, which is a 5-spot gas and water drives. You have Rappaport, Carpenter, Lees, which is a linear and 5-spot behavior relationship investigation. You have Higgins and Layton. Streamline channel flow method, a pattern, which is a number of parallel flow tubes whose boundaries are the streamlines generated by unit mobility ratio. And then you have mathematical models, such as Douglas-Blair-Wagner, which is capillary viscous effects, simulated linear model. Hyatt, which is vertical coverage, vertical sweep attained by water flood in a stratified reservoir. You have the Douglas-Piesman-Rushford method, which is relative perms, fluid viscosities, densities, gravity, and capillary pressure. You have Warren and Cosgrove, which is mobility and crossflow effects in a reservoir whose perms are log normally distributed. And then you have Morel-Sato, which is a pattern geometry mobility ratio on water flood recovery. You have gravity and capillary effects are neglected. And then you have empirical methods, which is Guthrie Greenberger. 73 sandstone reservoirs combined with solution gas drive and a water drive. Oil recoveries related to perm, porosity, oil viscosity, formation thickness, coordinate water saturation, depth, oil reservoir, volume factor, area and well spacing. You have shower, which is based on the past performance to 5 flood and to predict water flood recoveries of the Illinois basin. Oil production response is a function of the Lorentz coefficient. Higher coefficient is lower oil production. You have the Guerrero-Erlanger. Oil production first begins when the injected water volume is from 60 to 80% of the gas filled in the reservoir space. Waterflood oil producing rates peak up immediately after the fill up and remain at that level for 4 to 10 months. The period of peak production will occur when the ratio water injection rate to oil producing rate ranges from 2 to 12, with values of 4 to 6 for a flood. The oil production rate will decline thereafter at a rate of 30 to 70% per year. And then you have the API statistical study of 312 reservoirs, developed correlations for water drive recovery from sandstone and sand reservoirs, and for solution gas drive recoveries from sandstones, sands, and carbonates. So water flood prediction methods could provide ultimate water flood recovery, composite reducing water oil ratio versus recovery, composite values of injection rate, producing water oil ratio, oil recovery, and injected water versus all versus time. Individual injection rates and cumulatives and individual producing rates, water oil ratio, and oil recoveries, all versus time. So you have factors affecting water flood recovery performance or recovery performance. Some of the questions you need to ask yourself. Is the reservoir likely to perform a series of independent layers or zones of different permeability with fluid cross flow? Are there zones of high gas saturation or high water saturation that could serve as channels for bypassing water? Does the reservoir contain long natural fractures or directional permeability that could cause preferential aerial movement in some direction? Are the areas of high and low perm that might cause unbalanced flood performance? Is cross-bedding present to the degree that fluid communication between injection and producing wells might be impaired? Is the reservoir likely to contain planes of weakness or closed natural fractures that would open at the bottom hole injection pressures? Some limitations for pilot water flooding. With a small pilot, the probability of locating it in a non-representative portion of the reservoir is increased. The effects of damaged well will be more pronounced with a small number of wells. Oil migration losses from a single pilot pattern may lead to an estimated recovery lower than that to be realized for a full-scale flood. Injected water may be lost outside of the pilot area, suggesting a higher injected water requirement than for full-scale water floods. But there's some information obtainable for pilot water floods. Typically a single 5-spot and single injection floods. It's a ratio of well diameter to the distance between injector and producer. The ratio of pressure drawdown at producing wells to the pressure increase at injecting wells. The effective producing rates and mobility ratio on a particular pattern. The effective initial gas saturation on a single injection well pilot. And then you have the condition ratio, which is the ratio of the flow capacity of the reservoir as determined by the productivity index data to the flow capacity determined from pressure buildup data. You have design considerations. So be located in a portion of the reservoir representative of oil saturation, perm, reservoir heterogeneity for the remainder of the reservoir. Be composed of a single or multiple 5-spot pattern with the producer stimulated so that they have a condition of 2.22 or above. Have injection rates for each injector proportional to the product of the porosity and net peak thickness of areas surrounding each injector. And that's everything I wanted to share with you all today relating to water flooding. Here are my platforms that you can connect with me on LinkedIn, Instagram, and Twitter. They're all the same, similar handles for each one of them. So feel free to follow me on Instagram, follow me on Twitter, and connect with me on LinkedIn. I am open for questions. Does anyone have any questions?
Ma'am, we have few questions in the chat box.
Oh, okay. What was the condition ratio in the last slide? Okay, let me. It's the ratio of the flow capacity of the reservoir as determined by the productivity index data to the flow capacity determined from pressure buildup data. Anyone else? I don't think we have any more questions. What is the effect of layering on imbibition? The effect of layering on imbibition would just mean that there might be some cross flow in terms of injecting to other targets with higher permeability. Yeah, I don't think we have any more questions. So this concludes the session. I really appreciate everyone's time, and I will see you all tomorrow. Bye.